Science Alliance. Hello, I am Lara. This is Theory of Science. I am actually trained to teach physics to A-level, so that is what I'm doing. I'm teaching you IGCSE physics, just all of the lessons, all in a row. It's going to take 2 years. We're actually skidding to the end of the first year. We're nearly halfway through this course, and today we're learning about ultrasound. Now, when you think of ultrasound, a lot of you are going to think of very cool animals like dolphins and bats. To start teaching you about ultrasound, I'm going to have to teach you how you use an oscilloscope, which is quite a long way away from the world of dolphins and bats. It's still important and it's still useful, and if you end up studying dolphins, you might well end up using an oscilloscope. So here's what an oscilloscope is, all right? I actually showed you a picture of it, I think, in last week's lesson, but I didn't explain it at all. An oscilloscope is a machine that can be used to display sound waves. So I've said before, hopefully by now you're fairly comfortable with the idea that sound waves are not waves that traditionally look like this. There's not a great way of modelling them, but for our purposes today, we're going to show them as those uppy-downy transverse waves. So you've got a sound, right? I think this is a real IGCSE physics question. You've got a sound. You want to display it. You want to be able to actually look at the sound wave. So what do you need? Well, you need an oscilloscope. That is a word that they will expect you to know. That takes sound that you can hear and turns it into something that you can see. You would need a microphone and some wires. Oh, I just gave me the answer, blooming heck. Oh, that's really annoying. Yeah, I was going to say, you've got an oscilloscope and you've got some wires. What else do you need? Because it was amazing how many people on Facebook didn't know this, but yeah, okay, fine. You need a microscope, all right? Sorry, I'm sorry that I deprived you of brain exercise there. But if you want to look at a sound wave, instead of just hear one, you need a microphone and wires and an oscilloscope. People on Facebook yesterday were saying things like a speaker, which I thought was a good point to make. You don't actually need a speaker if you're going to look at a sound wave. A speaker will play you, like an amplified sound wave, will play you the sound of a sound. But to just look at it, technically all you need is a microphone to record the sound, for the sound wave to go into, and wires and an oscilloscope. We'll talk about signals in another lesson, which will make sense of the bit in the middle. But there, that's the kind of setup that you want. So it looks really scary and complicated, right? But actually on the oscilloscope, you're only going to be using a few dials. You obviously, to pass your GCSE physics exam, your IGCSE physics, you don't need to use an oscilloscope at all, but you do need to know how it works. So we're really only just going to be using this dial here, actually, that says X position and time/div. So let's say you plug a microphone in and you play a steady note. The sound wave that you see on the screen, it's basically a graph. So the x-axis, the up and down axis here, is the amplitude. That shows you how far away the peak or the trough is getting from the midline. And the x-axis, be careful here, the x-axis is time going by, all right? So it's a graph with amplitude on the y-axis and time going by on the x-axis. This little time/division knob, well, that means the amount of time per division. I might just I'm just going to let you look at that for a few seconds. I don't need you to understand it, but rather than just me kind of barreling on and telling you what's happening without giving you time to work it out yourself, just have a little look at that knob, time per division. Like, what do you think that means? Any idea? You're on your own in a room with an oscilloscope, you've been told to work out how it works. What are you going to do? What are you going to twist? What are you going to change? You literally don't even have to do any thinking. I just want you to look at it. Just take it in. All right, let's have a look at it together then and see what these things actually mean, see if we can make sense of all these numbers and letters. So each of these squares is a division, okay? That's what the division means, these lines that are dividing up the whole screen into squares, I suppose. This is an S here, which means seconds, and this is a little m, big S here, which means milliseconds. All right. You may or you may not know that there's 1,000 milliseconds in 1 second. So if you turn this line here is like a knob, and you could turn it so it's pointing at 5 seconds per division, or you could make it so that it was 2 seconds per division, 1 second per division. You keep making it less and less time per division until you get here, and then it's 50 milliseconds per division, 20 milliseconds, 10 milliseconds, okay? So at the moment, it's pointing straight upwards, and it's telling us that the amount of time per division is 0.1 seconds. Each division here is 0.1 seconds. So they won't actually write this on, but you can imagine that each one of these divisions, if this is 0 in the middle, is 0.1. So it's just like any graph. It goes 0.1 seconds, 0.2 seconds, 0.3 seconds, 0.5 seconds, blah, blah, blah. If you then turn the knob to 5 seconds per division, then it's just the same thing. You've just changed the scale of your graph. So that would be 5 seconds, and then that's 10 seconds, 15 seconds. So you want to be able to display the wave on the screen. So you basically just kind of turn the knob until you've got a neat looking wave on the screen, and then you can start to read things about the wave. Let's do a little reminder. Hopefully, if you've been watching the previous lessons, you're pretty comfortable with what wavelength is now, but I reckon there's one you might have forgotten. So wavelength is just the length in meters of one full wave, right? Wave length. There's no tricks there. So here we've got, I mean, we've talked about how you can measure wavelength from peak to peak, so from there to there, or from trough to trough, or you could measure it from the midpoint, go all the way up, go all the way down, and when you start repeating yourself, that is one wave. So what's the wavelength of that wave? Go on. You've got the x-axis showing you the distance. That's important. You would need to know that. So that's the distance. And you've got 1 wave, 2 waves, 3 waves, 4 waves. So the wavelength of that wave is 3 meters, right? It goes all the way up, it goes all the way down again, and then that's 1 wave. So that's 3 meters. Or if you didn't like where I put the 3, you could have said, well, I'm pretty sure that's 1, 2, 3, 4 waves in 12 meters, and then you could have divided it by 4. All right. Frequency is how many waves per second. I've mentioned that quite a lot as well. So frequency is measured in hertz. Hertz literally just means per second. So how many waves per second is being shown on the screen here? What's the frequency of that wave? It goes all the way up, all the way down, all the way up, all the way down, and then 1 second we say has passed. And then it goes all the way up, all the way down, all the way up, all the way down, and then that's when 2 seconds has passed. What's the frequency of that wave? How many waves per second? Well, let's count them, because all the way up, that's 1 wave. And that's the other one all the way down, and then 1 second has gone by. So that's 2 waves in 1 second. 2 waves per second. Frequency of 2 hertz. This is the one that I'm thinking you might have forgotten. Period. Period is how long it takes a wave to complete 1 full cycle. So again, here we've got a wave going all the way up, all the way down, all the way up again, and that's after 2 seconds, and then it goes all the way up, all the way down, all the way up, and then that's after 4 seconds. So we've got another x-axis here where the time is in seconds. What's the period of that wave? Period is measured in seconds, because it's how many seconds it takes for a wave to complete a full cycle. So the period of that wave is 2 seconds, right? It's taken 2 seconds for 1 whole wave to complete a full cycle. Okay, let's see how well we understood that, shall we? We've got an oscilloscope trace here. It's 0.1 seconds per division, so it goes 0.1, 0.2, 0.3. You've got the wave going all the way down, all the way up again, and then all the way down, crossing the x-axis where it says 0.5. Which of these statements is true? Is the wavelength of that wave 0.5 meters? Is the frequency of that wave 0.5 hertz? Is the time period of that wave 0.5 seconds? Which one of those is correct? It's a good question, isn't it? I was happy with this. Good way to check if you've taken in everything that I just told you. Which one of those is true? Is maybe more than one of those true? Ooh, is more than one of those statements true? Well, hopefully you're not saying wavelength, because the x-axis, remember, the x-axis is not in meters. That's not a distance. This is the amount of time per division here, 0.1 seconds. So you don't know the wavelength of that wave. You haven't got the distance in meters. And it's not the frequency either. Frequency is the amount of waves per second. It's the time period. Time period is the amount of time it takes for one full wave cycle. So we've got one full wave there going all the way down and all the way up again, coming back after 0.5 seconds, because the time per division there is 0.1 seconds. Is that okay? All right. So yeah, the x-axis on an oscilloscope is showing time going by, not wavelength. All right, I'll give you an example, and then I'm just going to ask you loads of questions to check if you've understood that, okay? So 1 centimetre, one division on this trace is 1 second. There you go. So you can picture those little lines on the graph as being 1 second each. So the time period of that wave is 5 seconds. It takes 5 seconds for one wave to go by. Okay, what's the time period of this wave? So your time per division knob is pointing to 1 second. And you've got a wave. The peak of the wave is crossing where x equals 0. It's going all the way down and all the way up again after 1, 2, 3, 4, 5 divisions. What is the time period of that wave? How long has it taken a wave to complete one complete cycle? Well, let's have a look. It's on 1 second per division. So each of those little dividing lines represents 1 second. So we could label them in our heads to make things easier. So that wave is going, we measure wavelength from peak to peak here. So the peak comes back after 5 seconds. So the answer is 5 seconds. Is that okay? It took 5 seconds for that wave to complete one full wave cycle. All right, next one. So this time your time per division is on 2 seconds. And you've got the same wave actually, starts at the peak, goes all the way down, goes all the way up again after 1, 2, 3, 4, 5 divisions. What's the time period of that wave? I told you to bring a cuddly toy with you. We will use it in a second, but I must say I'm quite enjoying just having a cuddly toy with me. I'll just start bringing this apple to all my lessons. Have you done that one? Okay, so this time each line is representing 2 seconds. So this time from peak to peak is 10 seconds. So it's taken 10 seconds to complete one wave cycle. So it looks the same, notice, as the last one, doesn't it? It looks pretty much exactly the same. So you've got to be really careful that you note how many seconds there are per division, because you can display different waves on an oscilloscope as looking the same by just turning the knobs. So that last question was 10 seconds, all right? What about this one? Oh, it's fun. It crosses at the peak of the wave, crosses the x-axis at 0, and then it goes all the way down, all the way up after 1, 2, let's say 3 divisions. Not perfect, this is it. And then all the way down, all the way up after another 1, 2, 3-ish divisions. And the time period, again, it's on, the knob is on 2 seconds per division. All right, let's have a look. It's 2 seconds per division. So we can picture each one of these divisions as being 2 seconds. And we've got 1, 2, 3, oh yeah, beg your pardon. 1, 2, 3 divisions there, but each division is 2 seconds. So the answer is 6 seconds. If you notice that peak isn't quite crossing that line, is it? And you said like 5.8, then well done. That would be fine as well. What about this one? So this time the very middle, the midpoint of the wave is crossing the x-axis at 0. It's going all the way up and all the way down and all the way up again, and it's hitting where the y-axis equals 0 at 1, 2, 3, 4, after 4 divisions. And the time per division knob is on 10 milliseconds. Have you done that one? Should we have a look? So it's on 10 milliseconds per division. So each one of those divisions is 10 milliseconds. So it's 1, 2, 3, 40 milliseconds is that time period. Could you convert that into seconds if you had to? They might well ask you to do that. That is maths that you will have to do. 40 milliseconds in seconds was 1,000 milliseconds in 1 second, right? Some of you will just know this straight away. If there's 1,000 milliseconds in 1 second, what's 40 milliseconds in seconds? If you've got to convert that into seconds. Well, 1 second is 1,000 milliseconds, right? So we've only got 40 milliseconds here, so it's going to be a much smaller number than 1. It's going to be fewer seconds. So what you have to do is you have to divide 40 by 1,000. Do you know how to do that? The easiest way... I'm not a maths teacher, but the easiest way I think to do it, if you need to do it quickly in an exam, is, let me write backwards on the board, if you've got 40 milliseconds and you want to divide that by 1,000, picture the decimal place here, because that's where it is. That's like 40.00000, however many zeros you want, milliseconds, isn't it? To divide that number by 10, you would just move the decimal place back 1 space. To divide it by 100, you move the decimal point back another space, so that would be 0.4. But we're dividing it by 1,000, so we need to move the decimal point back another place, like that. And then put our zeros in. So 40 milliseconds is 0.04 seconds. Is that okay? Here we go. So you need to practice that bit if you're going to do an IGCSE physics exam. But this lesson is about ultrasound, isn't it? What are we talking about oscilloscopes for? Well, they will come back at the end of the lesson. But finally, let's talk a little about ultrasound. Well, ultrasound is basically sound waves so high humans can't hear them. Last week we talked about basically just this memory game. You have to know that you can hear sound waves, or humans can hear sound waves in general, of frequencies from 20 hertz, very low, only 20 waves per second, to 20,000 hertz, 20,000 waves per second. That's a lot of waves. Anything over 20,000 waves per second, that counts as ultrasound. Humans can't hear it. It's not a very scientific definition, I suppose, really, is it? Because it's just defined by human hearing. Anything over 20,000 hertz is, to us, ultrasound. So when ultrasound hits a boundary, some travels into the new medium, but some of it is reflected. Are you all right with all those words? We used those words a bit last week. So are you okay with the fact that a medium is just kind of stuff? So air is a medium, glass, water is all a medium, and a boundary between mediums. We talked about this a bit, didn't we, when we talked about refraction and things like that. We've talked about stuff going from air into water. So the boundary is like the dividing line. So when ultrasound hits a boundary, let's say that this is a glass window and this is an ultrasound wave. Some of it travels into the new medium, for example the glass, but some of it is reflected off the boundary like that. And bats know this. I mean, they probably don't know that, but they can intuitively tell, and they use this, same as dolphins do, to emit ultrasound and find prey, right? So a bat emits an ultrasonic wave, and some of it is absorbed by the moth, but some of it bounces back from the moth to the bat, and the bat just naturally uses this returned sound to gauge how big the thing is that it's just bumped its sound wave into, and also how far away it is as well. But humans can also do this. Humans use ultrasound to locate things. That is, in fact, exactly what sonar is. So a piece of equipment called a transducer is, say, on a ship, gives off an ultrasound wave into the sea. It's not good for sea life, but it's good for us. And then this bounces off, say, a submarine or something, and then gets back to the ship. And the transducer not only gives off the ultrasound waves, but it also detects that ultrasound wave when it comes back. And the time it takes to bounce back tells you how far away the object is. There you go, very much like a bat. Right, grab a little ball or a soft toy. It's a bit silly that there's no sort of activity that I could think of that would genuinely help your understanding for ultrasound. But I thought this might just like lodge its, not the actual toy, but this idea might lodge itself into your brain and might help you to remember something in an exam. I want you to imagine, and you can do this with me if you like, I want you to just imagine that I'm throwing this soft toy up in my house, hitting the ceiling, and then it's falling back down again, all right? And we're going to say that this toy is travelling at 1 metre per second. Obviously it's not. We'll just pretend. Pretend the toy, for easy maths, is travelling at 1 metre per second. And it's hitting my ceiling, and then it's coming back down again. Okay? I want you to tell me, how high is my ceiling? Are you ready? I'll start my little apple at the bottom of the screen. I'm just going to throw it up. It's going to hit the ceiling. It's going to come back down again. I'm going to count the seconds. It's travelling at 1 metre every second. How high is my ceiling? You ready? And you can do this with me if you want to. Let's go. 1, 2, 3, 4, 5, 6, 7, 8. How high is my ceiling? Let's do that again because it was fun. 1, 2, 3, 4, 5, 6, 7, 8. If this apple is travelling, oh, it's so cute, at 1 metre per second, 1 metre every second, how high is my ceiling? So some of you will be shouting, okay, it took 8 seconds, so my ceiling is 8 metres high. And some of you will be saying, no, it took 8 seconds to go all the way up and come all the way down again. So my ceiling must be 4 metres high. It went 1, 2, 3, 4, travelled 4 metres in those 4 seconds, hit the ceiling, so my ceiling's 4 metres high, and then took 4 seconds coming down again. 1, 2, 3, 4, and that is correct. That is correct. But when you're in an exam and the clock's ticking and you're sweating and you've got loads of questions to go, you're going to forget to divide by 2. You're going to forget to divide by 2. So just picture whatever cute little toy you've got in your hand right now if you brought one, and don't forget to divide by 2. Let's have a little look at how it works, because they probably won't ask you about a toy hitting your ceiling. Here's a ship. The transducer on this ship emits an ultrasound signal, and 1.5 seconds later receives the reflection back. If the speed of sound in seawater is 1,500 metres per second, how far below the ship is the submarine? Do you get it? So you have to remember that the speed of sound in air is 340 metres per second, but you don't have to know the speed of sound in seawater, but it is 1,500 metres per second. So this ship gives off a ultrasound wave. 1.5 seconds later, it gets that back. If the speed of sound in water is 1,500 metres per second, how far below the ship is the submarine? Can you do that? I'll give you a few minutes to think about it, and then I'll just show you the answer. It was going to be an example, but it seems like a waste of thinking to not give you a chance to try it. I've even given you the equation. Distance equals speed times time. How kind was that? There's a couple of ways you could do it really. Do you know, that's so funny, I've been doing this for 5 years and I've just realised something. Every time I put a question on the board, the number slightly drops. Sometimes it drops a lot and sometimes it just slightly drops, like the number showing me how many people are watching. And then it goes up again. And I always thought, oh, people switch off because they don't like answering questions. But you're pausing it, aren't you? That's what you're doing. I can't believe I've only just realised that. And the number goes back up because people pause it to do the question. And then they unpause it when they're finished, I think. Huh. Maybe. Anyway, should we go through it? Because this was sort of supposed to be an example, really. Okay, what's actually happening? You've got a sound wave being given off by this ship. It's travelling down. It's coming all the way back up again, and it takes 1.5 seconds to do that, and it's travelling at 1,500 metres per second. And we're looking for the distance. We're looking for the distance between the ship and the submarine. So I'm going to write down distance equals speed times time. And what are the speeds and times that we want to put in? Well, I'll put in the speed, which is the speed the wave is going at, and the time it took to get all the way back to the ship, 1.5 seconds. Times those together, and you get 2,250 metres, but that's the distance from the ship to the submarine and back again, isn't it? We only want the distance from the ship to the submarine, so we've got to divide it by 2. And we do. So we get 1,125. Now what you could have done is you could have said, okay, if it takes 1.5 seconds to go there and back, then it only takes 0.75 seconds to get there. You could have done that and put 0.75 seconds in there. That would have been fine. Hopefully you would have definitely got the same result. So well done if you got 1,125. Well done if you didn't, but you're thinking, all right, I'm a little bit closer now to being able to answer these questions because I've got some more for you. Here you go. A boat. There's no diagrams here, but I would strongly recommend you draw your own diagrams. That's always what I would do because they'll try and catch you out, and it's only when you're drawing a diagram that you realise they've tried to catch you out. A boat sends an ultrasonic wave towards a shoal of fish and after 4 seconds receives a signal back. How far away from the boat are the fish? A boat sends an ultrasonic wave towards a shoal of fish and after 4 seconds receives the signal back again. How far away from the boat are the fish? And the speed of sound in seawater, to remind you, is 1,500 metres per second. And speed equals distance divided by time. And the second question, it takes 1 second for a bat to detect the reflection of its ultrasound emission. So how far away is the moss that it is hunting? And I've been kind of giving you the speed of sound in air has been about 340 metres per second, but you would have to know that in your exam. They give you a bit of leeway. If you've said that it's like 330, you get a mark, whatever your answer was. Are you okay with that? Can I show you my answer to the first one? I think I did it on the PowerPoint anyway. Well, I did. I'll just show you what I did. So a boat sends an ultrasonic wave towards a shallow fish, and after it feels like cheating, doesn't it? What an awful way of fishing using ultrasound. Anyway, after 4 seconds, it comes all the way back. How far away from the boat are the fish? So I did myself a little diagram, like I would do in my exam. Here's my boat. The sound wave went all the way down and came all the way back in. This time I've drawn on, it took 4 seconds overall, so it took 2 seconds to get there, and it took 2 seconds to come back again. And I've written distance equals speed times time, because it does. So my speed, because it's in salt water, is 1,500 meters per second. And this time I've said the time to get there is 2 seconds. You should probably stick to one method, because otherwise you confuse yourself. To get just to the fish took 2 seconds, because it took 4 seconds overall to come back. So I've done 1,500 meters per second times 2 seconds to give me 3,000 meters. And I don't need to divide that, do I? I don't divide that. You might have done 15,000 meters per second times 4 seconds to get 6,000 meters, and then divide that by 2 to just get half the distance. Are you all okay with units in these situations and how you can use units to check your answer? So you know how if you do 15,000 meters per second times 2 seconds, you're timesing the numbers together, but you can also think of it as timesing the units together. So we usually write meters per second like that, don't we? Meters / seconds. But I sometimes find it easier to picture it like that, meters per second. So we're doing meters per second times seconds. If you know a bit of maths, you know that if you're dividing by something and then timesing by the same thing, that they just cancel out. If you divide by seconds and then times by seconds, it's like they don't exist. So in that equation, meters drops out as being the right answer. So you can think, I'm looking for a distance and I've got my meters is my unit. So that's worked. All right. Okay, let's do then. I'll give you a couple of seconds to finish off the next one. So there's the answer to that one, however way you did it. And for the next one, I'm not going to bother to show you my awesome diagram. Oh, it is so awesome. Yeah, I will. So you've got this bat. It takes 1 second for the bat to detect the ultrasound wave that it gives off. So therefore, it takes half that time for it to actually get to its prey. So the time is 0.5 seconds. So distance is speed times time. This time we're just talking about air. So it's 340 meters per second times 0.5 seconds. So the answer is the moth is 170 meters away, which now I think of it, probably too far away, isn't it? Still, it's a physics lesson, not a biology lesson, so it doesn't matter. There we go. So again, just pick a method. You could have just kept the time the same and then remember to divide the final answer by 2. Whew, right, so the reason why we spent the whole first part of this lesson talking about oscilloscopes is because when humans are using ultrasound waves, it's incredibly useful to use an oscilloscope to see the wave, or like say the transducer, but to be able to see the wave coming back. And well, you probably know that ultrasound, kind of probably the most famous use of ultrasound is to sort of be able to see the fetus in the womb as the ultrasound waves bounce back. It's also incredibly useful to engineers. So if you've got to check something, I don't know, like a bridge, if you're checking a bridge to make sure that it's safe, there's no point like unscrewing all the screws to check them to then screw them back in again, because that might, I don't know, make it unsafe. So what they do is they use ultrasound to see if there's any cracks anywhere. So you would have the transducer here. Here's the transducer. Careful diagram here. Send some ultrasound waves into the metal. and then you would display what you saw on a screen. So what it would look like is, remember the wave's always reflected a little bit at the boundary. So if you were watching this on a trace, the first big wave that you see, that's the wave that you've given off. That's sort of where you can start reading from. And the sound wave would ideally travel all the way to the end of, let's say, the bolt. The bolt. And then come back again. So you get one wave at the very beginning, and you'd get another wave as it got right to the end, and another bit was reflected back. So if you get a trace like that, you know that everything's okay. But if there's a crack, remember, ultrasound waves get reflected at the boundary. So if there's a crack here, you've got a tiny little boundary maybe between, say, the steel and the air. So that sound wave is going to get reflected back. And then that ultrasound wave is going to travel on a bit more and get reflected again by the boundary between like the air and the steel. Do you see what I mean? So what you end up with is maybe a trace that looks like this, where the ultrasound has been reflected off the boundaries of the crack. So, and then you would know, it probably wouldn't be that big, but then you would know, okay, we've got a problem, there's something in the middle, there's some kind of boundary that shouldn't be there. When I was teaching this lesson 2 years ago, I was trying to find some kind of relevant example to show you, and it turns out that only a few years ago they found a 30-foot hallway sealed inside an ancient pyramid. I know, using ultrasound. You can't just crack into pyramids, can you? Because of the culturally sensitive reasons and also the curses. So they literally just got a transducer, stuck it on the side of a pyramid. I don't know if that's literally. But yeah, and it allowed them to kind of detect things that were inside the pyramid without having to actually go in. So they got a trace, I don't know, looks a little bit like this. So the first wave would be, here we go. I've done a little demonstration for you here. The ultrasound waves goes into pyramid. So the first wave to be given off, that's your first wave on the trace there, the first peak. The wave bouncing off the back of the pyramid, that would be the last one received. And then in the middle, yeah, they discovered that there was something in the middle. And it turned out to be a massive hallway. So the first line is the wave reflecting off the front of the hallway. And the second line is where more sound wave has travelled through the hallway and then been returned at the boundary. Is that all right? Now, I've got an absolutely dismal question. One of my lowest moments, I think, when it comes to me trying to write IGCSE past questions for you. Again, I was trying to make it relevant, right? And interesting. So, NASA use ultrasound to check for cracks in their solid rocket boosters. I don't think they don't even use solid rocket boosters anymore. But those types of things, they use ultrasound to check for cracks. So I did this question, and there's a couple of things horribly wrong with this question. One of the problems is the numbers are ridiculous. I mean, so you'll get a number that seems far too big. It is the right answer, even though obviously you would never get a solid rocket booster with numbers like this associated with it. The other thing is, I've asked you how wide the crack is. But I've assumed that the speed of the wave is the same the whole way through. Now that's a big mistake, isn't it? Because say this is steel. If there's a massive crack in this thing, then this sound wave is going to travel through this steel very, very quickly, like 5,000 meters per second. But sound travels a lot slower through air, remember? Because air is a gas, the particles are further apart. So the whole speed of the wave is going to change in the middle of the crack. So the whole thing is total nonsense. But let's just get from this question what we can. Okay, so I want you to just imagine that the whole crack is just steel. All right? I don't know why. Let's just say it's built like this. So that's steel, and all this is also steel. Okay? Okay? It's just for learning anyway. It doesn't have to be realistic. Here we go. She shouts defensively. An ultrasound pulse was sent through the casing of a solid rocket booster. The trace, voila, shows there is a crack in the case. If 1 centimetre, like 1 division, equals 1 second. How far into the case does the crack occur? And how wide is the crack? I think this is really difficult, even without my ridiculous numbers and my crack that is made of steel. I think this is a really tricky question. I am going to be silent for a bit and let you ponder it. All right, I'll show you what I've got for the first one. This is so embarrassing. I can't believe this is saved on YouTube forever. It's so embarrassing. An ultrasound pulse was sent into the case of a rocket booster. The trace shows there's a crack in the case. So this is the first wave to leave, coming back. And then this is the wave coming back from the very back of the solid rocket booster. So this is our crack here. I'm regretting putting the word crack so much in this lesson, but it's too late now. So 1, 2, 3, 4. We've got 4 seconds between the first wave and the start of the crack. So we'll just do distance equals speed times time. They've given us the speed, which is 5,000 meters per second. So I've done myself a little diagram here. I said, all right, it's 1 centimeter per second, like 4 divisions equals 4 seconds. So it took 4 seconds for this ultrasound wave to get to the crack and then come back again. So I'm going to do distance equals speed times time, which is 5,000 meters per second times 4 seconds, which is 20,000 meters. But I've used the seconds as being the amount of time it took to get to the crack and come back. So I have to halve that to get the distance just to the crack. So I get 10,000 meters, which is obviously completely ridiculous. How wide is the crack? How wide is it? I think this is really difficult. It's a very difficult question. You've got to decide whether you're going to divide by 2 or not, don't you? So let's see. Think it through and then I'll show you my thinking. Can I show you my thinking on it? Okay, so you've got a distance between the two waves here. Like that wave's showing us where the start of the crack is, and that's the back of the crack, right? So the distance between the front and the back of the crack is 2 seconds. So I'm assuming that most of you probably did, all right, well, distance equals speed times time. The speed that it's travelling through the steel in is 5,000 metres per second. So I'll do that, 5,000 metres per second times 2 seconds equals 10,000 metres. But do I divide that by 2 or not? Now you might have been thinking, well, the distance between the waves is just going to be the distance between that's going to be the distance of the cracks, so that's fine. Let's have a look. So I would, this is what I would literally do in an exam, I think, if I was trying to think it through. You've got the transducer here. It's giving off a sound wave. Let's make this crack a bit wider. This is the big crack, okay? So the transducer emits an ultrasound wave, which hits this boundary between the steel and the crack. Some of this wave is reflected, right? And some of this wave carries on. So while this bit of the wave is carrying on through the crack, while that's happening, this bit of wave is travelling back. And then this sound wave here hits the back of the crack, can't say that too many times, so travels back. And while it's travelling back, this bit of the wave has travelled that distance as well. Did that make sense? The diagram now makes no sense, but hopefully while I was doing it, it made sense, right? We've got a sound wave gets to the crack, some of it is reflected back while the other bit goes straight forwards. And then, so this reflected wave here that's travelled through the crack has got to there, and this wave has got all the way back again. So that shows me, okay, I do have to divide it by 2. Is that all right? Because it's had to go there and back again. So the distance between those waves is going to be twice the distance of the crack. So I need to divide it by 2. So I'll get rid of that because I'm clear now. And the answer is 5,000 metre wide crack. Yeah, makes sense. Nailed it. Brilliant. Thus ends the lesson. It's not about me. It's not about me and making things realistic. It's about you and whether you've understood things or not. So hopefully you have. Right, chums. I'm going to go over to my Facebook page, because whenever I'm live on YouTube, there's no comments. YouTube's just stopped letting comments on for some reason. It did for a little bit, didn't it? But whenever I'm live on YouTube, on Facebook, there's always a little post saying, if you want to ask me any questions, or just say hello, let me know that you're watching, then do please feel free to comment, and that'll be lovely, and I'll say your name and say howdy to you. So yeah, that's the end of the lesson. We've only got, it's only 3 more wave lessons left now, and then it's the summer holidays. And then we'll be starting a whole new module when we come back. I love the start of a new module. I love it when there's loads of new people there and everyone's on the same page and everyone knows the same amount. It's nice. Not the same amount, but, you know, at least I know that I can kind of start teaching from the beginning. So, yeah, just join me next week for 3 more weeks before the summer. Oh, I've got some comments. Yay. If you want to support me, if you're thinking that it's good that someone who's trained to teach physics to A-level is just teaching for free live into the internet with free printouts where she can answer your questions, then you can pay me. That would be lovely. In fact, that's the only way anyone in my family makes money at the moment, because we home educate. It's all worked out very well. So, oh, hello, Gus and Milo the cat. Nice! Gus is watching live. Oh, that's awesome. Hello. Oh, there's Abba. Is that Abba? Wait, it's only showing me. Oh, it's Arthur. Hello, Arthur. Hello. We're off to Wales this weekend. Not as exciting as his Japan trip at Easter, but he will catch up once we're home. Ah, nice. Hello, Arthur. Hello. I totally distracted myself, didn't I? Oh, Indy's here. Hello. And Bastian's here. Oh, thank you. You found a virtual oscilloscope. The one that I usually use wasn't working, so that's really useful, actually. Thank you. I might link that to people in the homework. Hello, Freya. Oh, lovely. That's nice to know. And of course, there are lots of you lurking as well. And I fully appreciate your lurking-ness. That is great. I always say, like, these lessons really only work because some people give me amazing feedback and some people just leave me alone. If you were all give me loads of feedback, it would be too much. And if you were all lurking, that would be kind of creepy. So just between you, you found the absolute perfect balance. You should all just keep doing exactly what you're doing. Thank you very much. Right, there's an extra comment here. Oh, it's Freya again. We thought the example could be used to measure an underground cavern. Cavern is just a much nicer word, isn't it? I should definitely, if I just change the wording. Where were you on Facebook? It's all too late now. It's all saved on YouTube, isn't it? Of course I should have said cavern. And then all the numbers would have worked out and I wouldn't have had to keep saying back of the crack. Anyway, 2 years' time, thank you. This lesson will be fixed, thanks to you. All right, you know, well, thank you very much for saying hello, and thank you very much for lurking. And if you want to support me, please go to my About section on YouTube, or you can go to where it says sign up on Facebook. If you go to my About section, you'll find this link to this website called Coffee, where you can sign up to support me with £5 a month, and that is all I need. I mean, you can send me £6 a month if you like. That would be lovely. But if you want to send me £5 a month, I'll still send you my diffraction glasses and the thing I wrote about how they work, and Theatre of Science magazine, 1 or 2 past issues of Theatre of Science magazine, which is ever so good, you know, it's ever so good. I know, because I wrote it myself. Very good. And I will see you next week. Thanks for all your support. I'm just refreshing my comments. I don't imagine there's any more comments. That was a generous amount of comments for an IGCSE physics lesson. Okay, you lot, I'll see you next week. Have a lovely time in Wales if you're going to Wales. Or if you're in Wales already. Yeah, bye.